Hey guys, in this first example, we're given a function that represents a golf ball's position. And we're asked to find its position, its velocity, and its acceleration at t equals 3 seconds. So if I'm given this position function, I understand that that's like our function that we're given here. There you go. And I know its velocity would be the derivative of that, and its acceleration would be the second derivative of that position function. So we're going to write functions for v of t and a of t, and we're going to plug 3 in for t for all three of the functions. So if I'm given s of t equals negative 16 t squared plus 36t plus 50, then I know that v of t is the derivative of that, and it's going to be, let's use the power rule, a negative 32 t to the first power plus 36. Cool, and while we're at it, let's find the acceleration. And the derivative of velocity, power rule again, it's just going to be negative 32. Cool beans. So my next task is to plug a 3 in for t into all these functions. So after substituting a 3 for t, I end up with a negative 144 plus 108 plus 50, and when I do all my work there, it is 14. So the position equals 14 watts, 14 feet above the ground. And then down here, I'll have the velocity. So v of 3 will equal negative 32 times negative 96 plus 6, so negative 90. And its velocity, so it's feet, and this is per, let's see, t is measured in seconds, so it's feet per second. And lastly, a of t, there's nowhere to plug in my 3, so the acceleration a of 3 is just going to be negative 32, and it's going to be feet per second squared. And that's our acceleration thanks to gravity in feet per second squared. In this next example, we're going to be finding the inflection points of this function. And I know that the easiest way to do this is to see where the second derivative changes signs. So the big mistake is people usually just find where the second derivative equals 0. Make sure that you're verifying that there's going to be a sign change for the second derivative. So to find the second derivative, we should start by finding the first derivative. What do we got? A 4x cubed plus 6x squared. Cool, easy peasy. Find the second derivative. And we got a 12x squared plus 12x. All right, so we need to find where f double prime changes signs, so I'm going to want to make a sign chart. So let's find where f double prime equals 0. I'm going to factor out a 12x, which would leave me with an x plus 1. So I know that f double prime will equal 0 when 12x equals 0, so when x equals 0, and when x plus 1 equals 0, so x equals a negative 1. All right, so I'll include those 2 points on my sign chart for f double prime. Remember, we're looking for where f double prime changes signs, so that's what I'm using in my sign chart, right? F double prime. I've got a negative 1, I've got a 0. We'll pick some test points. Let's pick a blah, 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 blah. Let's pick a positive 1 and throw it in here. Positive 1 will give me a 12. Positive 1 here will give me a 2. So positive times a positive, totally a positive. Let's pick a test point of, I don't know, negative 2. If I pick a negative 2, then I'll have a negative 24, and a negative 2 there will give me a negative, so I'm working with a negative, and a negative make a positive, so positive in that interval. And let's pick somewhere between the two. Let's go with negative 1/2. If I use a negative 1/2, I will get a negative 6 there. If I use a negative 1/2 here, I'll get a positive. So negative times a positive. There we go. beautiful sign chart. So I see I do have a sign change at -1, and I do have another sign change at 0. So in my inflection points will be when x equals -1 and 0. And we're saying that f has inflection points at x equals -1 and 0. The reason is because f double prime changes. And we should be specific. We should say that at x equals -1, that we're changing from a positive to negative. And I should say that at x equals 0, f double prime changes negative to positive. Cool. Thanks for watching. See ya!